In this lesson, we're looking at related rates. So during the lesson, we'll start by defining what related rates are and how we're going to work with them. We'll look at the processes and components used and required to solve problems with related rates, and then we'll look at a few examples applying this process. Okay, so the first thing is defining what related rates are. Now, it's pretty straightforward. We're looking that if we have some rate, and let's say our rate is dy dx, a change in y with respect to x, if there is a third variable that they are related to, so let's say we introduce a parametric variable t, then we can write a rate that brings in this third variable. So dy and dx can be split, and we can fit in the third variable t in those vacant spots. So what that does, it doesn't change the equation. It's still the same thing. We could cancel out those dt's and we would still have dy dx. But at the same time, we can say that dy dx is equal to the product of dy dt, the rate of change of y with respect to t, and the rate of change of t with respect to x. So dy dx is our original rate, and this is our product, which consists of two rates related to the original rate. Okay, so I mean, this one we could pretty easily put into a scenario. We have, for example, a space that consists of x and y dimensions. So we have a height here that at any point is y, and we have a height here that at any point is x, and we have a plank that goes between them. So as this side moves at dy dt, so a rate of change of y with respect to time, we'll get a related rate dx dt. Okay, so those two can be related, and we could also look at the rate dy dx, the way that y moves with respect to x. Now, if we want a simpler example, a place that most people start with related rates is looking at a circle increasing with a set rate of change. So, for example, we can look at a circle with a radius r and an area which is given by pi r squared, and we can say that the rate of change of the radius is 2 centimeters per second. So that means the radius is getting larger at 2 centimeters every second. Now, to turn this into a related rates question, we may want to find out what the rate of change of the area is at a certain point. So let's say when the radius is equal to 10 centimeters. Okay, so this is a pretty standard question. We are looking for dA dt, and we need to set dA dt up. So we've got some related rates that include dr dt, the rate of change of the radius with respect to time. So it's pretty easy to do. We've got dA and dt, so we split that one, and we fill in with our third variable dr. And so now what have we got? We've got dA dr, which is the rate of change of area with respect to the radius, and we've got our dr dt, which is what we were given. Now this takes us to what do we actually need to solve a problem with related rates. Number one, obviously, is a given rate. So we need to know a rate to be able to work out the others. The second thing that we will need is a rate that we're required to find. So in this case, it was at dA dt. And the third thing that we will need is a rule that relates them. So in this case, what we're going to need is a rule that relates the area and the radius. And here it is here. There's that rule. Okay. To go along with that, the last thing that we'll do is we'll need to find the derivative of the rule to get the rate, and we'll need a value that we can sub in. So a value to sub. Now, as long as you've got those things, it's pretty straightforward. So if we were going to finish this question for this example, we're going to need dA dr. So dA dr will be the derivative of pi r squared, and that will be 2 pi r. And if we put this all in, then dA dr is 2 pi r, dr dt is 2, that was given. And so now we've got a rule of the rate of change of area with respect to time, and it is 4 pi r in this case. Now, as we're looking for when r is equal to 10, it's pretty straightforward. We can put that in. R is equal to 10, and the rate of change of area with respect to time is equal to 40 pi centimeters squared per second at that particular point. So if we take the same approach into any related rates question, the complexity only differs when we have to look at more complex scenarios, or we have to define equations from a scenario ourselves. So we'll start by looking at simple scenarios and we'll build up to more complex. So the first one is an application of what we just talked about. We've got a circular oil spill. It's constantly increasing in radius by 2 centimeters per second, and we're trying to determine the rate of increase in area after 5 seconds. So straight away, we know that the radius is increasing by 2 centimeters per second, so we know straight away dr dt is equal to 2. We're trying to find the rate of increase in area, so dA dt is what is unknown. And we also know that the area will be pi r squared. Now, because we know that dA dr, the derivative of a with respect to r, will be 2 pi r. And we know that we're looking at the radius being equal to 5. Okay, so let's work out what the related rate is. dA dt is equal to, so we'll split this dA and dt. We'll fill in the radius, so we've got our dr in each. We know that dA dr is 2 pi r, and we know that dr dt, which was given, is 2. So we've got our 4 pi r in this case, and it will be centimeters squared per second. And as we know that the radius is equal to 5, 4 pi times 5 will give us 20 pi centimeters squared per second after 5 seconds. Okay, so we can see this is pretty straightforward in this scenario. It's a rule that we knew, and it was easy to apply. When we look at example 2, we're again given a rate. So a rectangular prism is being filled with water at a rate of 0.00042 meters cubed per second. So that means that we're filling at a rate that's a volume, dV dt is equal to 0.00042. We want to find the rate at which the height of water is increasing, so we're trying to find dH dt. And when we're looking at a rule that relates volume and height, then basically we're looking at this volume rule where we've got volume is equal to length by width by height, where we know the length and we know the width, and the height is a variable. So we've got 3 by 2 by h, and therefore we've got 6h, and that's our v. From that, we should be able to say that dV dH is simply equal to 6, so it's a constant rate. So this one's a nice easy one to work out. We're trying to find dH dt. Now, if you have to choose which one goes first, it's generally the one that has the rule. So we've got a rule of v with respect to h, right? So we want to start with this dv dt, and we want to expand that out. Okay, so dv dt is equal to, now we split the dv and the dt, and we'll fill in the third variable, which is a h, so we've got our dh in there. So let's fill in everything we've got. We've got dv dt, which is 0.00042. We've got our dv dh, which is 6, and our dh dt is what we're trying to find. All right, so the last step is that we want to isolate, so dh dt will be equal to 0.00042 over 6. And so that means we end up with 0.00007 meters per second. Okay, so again, nice and straightforward. Remember, it comes down to these 1, 2, 3. Okay, so example 3. Now we've got a metal cube is being heated so that the side length is increasing at a rate of 0.02 centimeters per hour. We want to calculate the rate at which the volume is increasing when the side length is 5 centimeters. Okay, so we know that the side length is increasing, so we'll say that's dx dt at 0.02 centimeters per hour. We're trying to find that rate of increase in volume, so we're trying to find dv dt. And if we draw ourselves a diagram, now we've got a cube, and so x is that important variable there, and we know that the volume of a cube is x cubed, then we should be able to go, well, dv dx will be 3x squared. So we need that, and we know that the side length x is equal to 5 is when we want to solve this. So we want it in terms of the rule that we had, which is v is equal to. So we want to say that dv dt is equal to, split our dv and our dt, and we fill in our third variable dx. dv dt is what we're trying to find. dv dx is 3x squared, and dx dt is 0.02. Now x is equal to 5, so we've got 3 times 5 squared, and 0.02 is 1 on 50. So we've got 3 times 25 over 50, which ends up being 3 on 2 centimeters cubed per hour, or 1.5 centimeters cubed per hour. Okay, so if we look at this next example, we've got a diagram that shows a rectangular block of ice that is x centimeters by 5 x centimeters. We want to express the total surface area in terms of x, and then we want to find dA dx. So part A is breaking it down for us a little bit in this one. So surface area, we'll have 4 lots of this 5x by x. So 4 lots of 5x multiplied by x. And we've got 2 ends, so 1 end, 2 ends, and they will be x squared. So we've got 20 x squared plus 2x squared, which gives us a nice easy 22x squared for our surface area. And we'll call that A, because that's what they told us to do. And we'll then find dA dx, which ends up just being 44x. Now part B, they say if ice is melting such that the total surface area is decreasing by a constant rate of 4 centimeters squared per second, so that means we're going dA dt is decreasing, so it's negative 4 centimeters squared per second. And what we want to find is the rate of decrease of x, so dx dt is unknown. So we'll split this up. Remember, we use the one that we've got the rule for. So we've got the rule a is equal to something x. So dA dt is equal to, now we split the dA and the dt. We fill in our dx, and we have 44x multiplied by dx dt, which is our unknown, will be equal to -4. Now we know that when x is equal to 2, so that means we have -4 is equal to 44 times 2 times dx dt, and therefore dx dt will be equal to -4 over 44 times 2, and so that means we'll end up with a nice easy dx dt decrease of -1 on 22 centimeters per second. So again, it was a nice easy application when we broke it down into the right pieces of information. Now the last one's going to be the most complex. We've got an inverted cone. It has a height of h centimeters, radius of r, is being filled with water which is flowing from a tap at k liters per minute. The depth of the water in the cone is x centimeters at time t. Construct an appropriate differential equation, dx dt, and solve it given that initially the cone was empty. Okay, so this is telling us that it's been filled with water which is flowing from a tap at k liters per minute. Now, because we're looking at centimeters, we know that 1,000 centimeters cubed is equal to 1 liter. Okay, so that's saying that we're filling out 1,000 cubic centimeters per minute. So dV dt, 1,000 K. dV dt is 1,000 K cubic centimeters per minute. So we've got one piece of information there. Obviously, we're going to be looking at a scenario where dV dt is equal to dV dx and dx dt. Now, if we want to be able to solve this, we need to think of what we've got here. And the tricky part is seeing that we've got these similar triangles. So there's a rate relationship here. So this is r, and this is x, and this is h. We can find a relationship between these, and the last variable, the unknown, will be this a value here. And now obviously that a is really important because that allows us to calculate the volume at any point in time. So that volume is equal to 1/3 pi r squared h, where r is an r in this case, it's a. So 1/3 pi a squared, and it's not h, it's x. So that's the general rule. This is our rule for this case. Now, we can't actually differentiate this because what we're looking for is dx dt. And at the moment, we've got a squared in there, which we cannot have. So we need to be able to get rid of this a squared. So we need another relationship, and that's where our similar triangles come in. We can say that the ratio of h over r will be the same as the ratio of x on a. So we've got our small triangle, our large triangle, and our similar triangles, they've got those same angles. So 1, 2, 3 angles AAA, we can prove they're the same. Now we want to be able to replace a squared, so if we flip these ratios, we've got r on h is equal to a on x, and therefore a is equal to xr on h. As r and h are constants, then that's fine to be able to sub these in. So that gives us the volume is equal to 1/3 pi xr on h squared x, and that's 1/3 pi x cubed r squared on h squared. Alright, so now we've got our rule for v. And if we set that up with that variable separate from the constants, we've got volume is equal to pi r squared on 3h squared multiplied by x cubed. And therefore dv dx will be multiplied by 3. So that cancels the 3. And we've got pi r squared on h squared multiplied by x squared. Alright, so now if we put this in, we have dv dt is equal to, we have dv dt, which is equal to 1000 k, dv dx, which is pi r squared on h squared multiplied by x squared, and dx dt is what we're trying to isolate. So multiply by h squared divided by pi r squared, and we're left with dx dt is equal to 1000 k h squared on pi r squared x squared as our differential. Now it says construct an appropriate differential equation for dx dt and solve it given that initially the cone was empty. So that's when t is equal to 0, we know that x is equal to 0. So in order to solve this, now we have to go through our differential process. We'll multiply across this x squared. So we've got x squared dx, and we've got 1000 k h squared on pi r squared dt. So this is 1/3 x cubed and 1000 k h squared t on pi r squared plus c. Now when t is equal to 0, x is equal to 0, so what do we get? We've got 0 is equal to 0 plus c, so c is equal to 0. And we end up with our rule, x cubed is equal to 3000 k h squared t on pi r squared. Now I could make it an explicit equation and take the cube root, but I'm going to leave it there as I think that's an appropriate solution. Okay, so we can see that jump up in complexity. This is much harder. There's many components. We had to create the differential and solve the differential, and so we end up with a specific solution with a number of parameters. We don't know the height, we don't know the rate, we don't know the radius, and that allows us to have this general equation to utilize in a number of different scenarios with different sizes and so on, and rates and flow rates and so on. So hopefully that makes sense. Most of the questions should be relatively easy, but of course we can have these complex, unfamiliar ones. Thank you.